All right, welcome back. We are GAME3001 in the winter 2022 semester at George Brown, and it's week 5, part 1 of our broadcast and recording. And not for today, Shelley. And this week we're talking about pathfinding. We're talking about two types of algorithms that we're going to be kind of investigating. One of them is called Dijkstras Algorithm, and the other one is Astar pathfinding. Okay, those are the two algorithms we're going to be investigating this week. So it's kind of an intro into pathfinding. Okay, there's other ways of doing pathfinding, but those two algorithms are the things we're going to look into this week. But before we start, let's get into some stuff. What did we do? This should say last week. Haha. I love this when I make a mistake. So last week we talked about combining steering behaviors, flocking, what that looks like, and flocking was kind of an output of combining two steering behaviors, right? We talked about things like separation, which is kind of a type of flee, that's what it is, and cohesion, which is a type of seek, right? So it's kind of a combination of seeking and fleeing and arrival, right? So those three things to produce a separation, and yet, for the flock to remain coherent and together, aligned. Alignment is another one that we used, right, in the same direction. So that is flocking. We didn't do a flocking example in the lab, but it's very interesting. If you're interested as an academic, if you're interested to learn about flocking, I think there's some great stuff online to take a look at it and investigate it on your own. Fantastic stuff, and really fun to look at. We also talked about problems when steering behaviors are in conflict, what that means. A lot of times it's when one steering behavior is telling you to go one way and the other steering behavior is telling you to go the other way. You're combining two actions. A good example of that is what we did last week with obstacle avoidance. On one hand, we want to steer our autonomous character, our agent, towards the goal, whatever that is, the target. And at the same time, we're trying to use our AI sensing array, which is really just a bunch of whiskers, or primitive pathfinding, primitive raycasting, in order for us to kind of determine that there's an obstacle in front of the autonomous agent and that they should move away from the obstacle, but at the same time move closer to the target, right? Which is kind of the conflict, right? How do you make that look good when you put together your assignment 1? So that's what we talked about last week. We did lab 3, which was we updated the agent class. We talked about adding whiskers to the agent class. We added an obstacle to the play scene, and we used whiskers to avoid collisions with the obstacle while dynamically seeking the target. We also did some work with IM-GUI, so hopefully you're more comfortable with the framework. That's what we're hoping, and with IM-GUI at this point, since you've done assignment 1. And let me just do some housekeeping now before we continue what we're doing this week. I wanted to talk about a couple of things that have come up in terms of frequently asked questions from you guys to myself and to Alex. Okay, so let me just clarify some stuff. First, labs are to be done individually. Okay, they're not to be shared. You're not doing them with somebody else. They're all individual marks, as we talked about this in the first class together, right? So please don't submit a lab and say that it's from me and these two people. That is not acceptable, and you'll be asked to do it again. Okay, so anyone who's done that, okay, it's unacceptable. We're not going to accept labs from more than one person. It's individual work to prove and to, for us to evaluate you, to know that you are participating A, and understand the algorithms B. Okay, those kind of things that's why we're doing labs. Okay, labs have no extension date. So if you don't get it done by the Sunday, there is no minus 20%. Either you do it by Sunday or you get 0. That's how it goes. Labs are meant to be in person, typically from an in-person learning perspective. And so when we're online, they represent the same exact thing. You're supposed to do it in class. Now, we can't do it in class because of restrictions, because of the pandemic. In real life, when we come back to class in perhaps in summer or in fall, the expectation is that you're going to be doing the lab together with the instructor and submitting it that night. That's how it goes. The extension you would get is from the time that we do it with you until Sunday. So that is really your extension. You have that leeway to submit it, worst case scenario, just in case you couldn't follow along quick enough and that kind of stuff. That is your extension. There's no more extensions. Please don't ask for, can I submit my lab? I was late. It was due on Sunday, blah, blah, blah. No, that's not how it works, okay? So don't ask for those things. Unless there's some kind of medical reason why you can't attend or something else, whatever, your lab is your lab. Okay, so that's number one, just clarifying here. Number two, assignments. Assignments are the only ones that you're going to do with someone else, a group member. If you sign up for a group, and by the way, please, we're going to talk about this in a second for this week. This week, when we're signing up for groups for assignment 2, that's due week 7, if you haven't signed up for a group right now, you need to re-sign up for groups for assignment 2. The groups for assignment 2 are different than the groups for assignment 1. Just because you signed up for a group in assignment 1 doesn't mean anything. You have to still sign up for groups for assignment 2, right? If you had a bad experience with partners from your group from assignment 1, do not choose them for assignment 2. Okay? And during the time that you select a group member for assignment 2 coming up, you are stuck with them. You cannot complain about them. You cannot say that they're not doing any work, right? Or anything like that. That's why we set up multiple groups throughout the semester, to give you a chance to move away from one group to the other if you're having a bad experience with somebody. We don't want anyone to have bad experience, so we're giving you 4 opportunities to switch groups, pretty much. Okay? Assignment 3 and 4 are kind of together, and that's where we're going to be a little bit, it's going to be a little different. Okay, so that's what's happening with assignments. Assignments, you do have a chance of submitting late, right? That follows the minus 20% rule, and you have 3 days max. After 3 days, it's 0. So you can go to minus 60, and then after that, you're done. Okay, that's how it works. Again, unless you have a medical reason for doing so, you must submit your assignments together with your team member. If one of the team members, for whatever reason, is not able to work with the other team, right, as an example, or the other team member, then unless there's a real good reason, you're stuck with those people. You're pulling your weight, okay? 20% per day late after the due date, Christian. That means if it was due on Sunday, let's suppose, right, then Monday is 20%. So that means maximum you can get is 80%. Tuesday is minus 20%. Maximum you can get is 60%. And Wednesday is minus 20%, maximum you can get is 40%, and after that, there's no point submitting anything. Okay, so that's how it works for the 3 days. Now, I'll be honest with you. Typically, right, I'm very lenient when I mark stuff, which means that when you submit your assignments, if they're pretty good, and if you're overtime a few minutes, right, or an hour, I'm not going to complain, because no one's perfect. I'm not perfect. You're not perfect. The system's not perfect. I have a leeway system in place. Even if you're late, if you're within a reasonable time frame, I don't, attack you and say, well, too bad, you're 1 minute over. I don't care. I don't do that. Obviously, I'm not a machine. I'm a man, right? Just like myself and Alex, and we're very reasonable when it comes to submitting your stuff. But again, asking for an extension the day of, as an example, for the lab because your lab partner is gone or something like that. I mean, remember, we're giving you weeks to do this stuff. This is not something we give you today, do tomorrow, and you need an extension. That's not the way it is, right? So the expectation is when we give you the assignment, on or around the date, you start working on it. Okay, that's how it works. And how does that work? Because we're giving you lab time to start working on your assignment. Anything we show you in the lab can be used word for word, line by line for your assignments if you want to. It's all fair game, right? That's why we give you those things. We give you an opportunity to build your lab, build your assignment through each lab that we work together on. All right, so I think those are reasonable terms when we get together for everyone to learn. The best way to learn stuff for AI is to do it. There is no better way. You can't watch somebody do it like me or Alex or your partner. You can't do that. You have to do it. You have to be engaged in it. You have to get your hands dirty, if you will. and just do that stuff. That's how we code. That's how we learn. People always ask, what's the best way to learn how to code? And the answer is code. There is no better way to do it, right? Just like when someone says of a writer, what's the best way to learn how to be a great writer? Write. You know, read. That's another thing. Reading code is good. Taking a look, doing some of your own research, those are all great things to do. And I think that's the way we want you to progress. So that is the way it is. One thing that I also want to mention is some precepts, things that we've talked about in the past is what is good enough. We're going to talk about that more and more as we're together through this whole journey from the time that we started together in first year all the way to the last year together at George Brown. We're going to be talking about that. We're going to say what is good enough, because we're going to come to the point where you're going to determine what is good enough. Whether you're a coder or an artist, we iterate through our creativity to build the things that we need to build. And then they're going to come to a point where we don't continue because we've done as much as we can given the time that we have and other priorities that we have. And that's why it's important to start early, iterate often, right? And continue to improve and work with your partner. One of the things I always recommend to everybody is communication, right? Good communication. You can't submit something on time for your partner. Tell them. Don't ghost them. If you're on Discord with them, or if you're using some other kind of communication medium, email, or, you know, God forbid, calling someone nowadays, then at the end of the day, make sure that you're available as you promised, right? That's how to be a good team member. And sometimes to be a really great team member is to pick up the slack when somebody's falling down or if they don't understand something, right? Pick your partner up. Don't push them down. Okay, that's not the thing here. When you're doing an assignment, you guys are a team, all right? And that's what the expectation is. It's a small team, but it's where you can build trust with you and another programmer to be better, not just as a programmer, but as a human being. Okay, so that is the expectation from us to you. Hopefully that clarified, because I know there was a bunch of questions and a lot of email that went back and forth that I did not answer. Just letting you know, because we had discussed it in week 1, 2, 3, and 4. And I'm talking about it again in week 5, right? So please, I expect you all to adhere to these things. I don't think they're unreasonable. You guys are all adults, every one of you. And I believe in you. I know you can do it if you participate and you have the best intentions in mind moving forward to better yourself and to become a game developer, which is why you're in this program. And because you love games, which is why I teach this stuff, because I love games and I love teaching programming to you guys, right? So let's work together, guys, and move on today. We have a lot to cover and very little time as always. So let's get going. I'm sure there's going to be questions. Guys, the best way to interact and learn for this stuff is to ask the questions during the lecture. We have a lot of time to do it together. Let's go. So that's what we're doing this week. We're doing Lab 4. It's going to start this week, but it's due week 6. Lab 4 is a lab that spans over 2 weeks, just like Lab 2, okay? And sometimes we have that thing happen. Let me take a look at that. In that, it says that in our structure, right? So Lab 4 is started, and then Lab 4 is finished next week. Why? Because there's a lot to code between this week and next week. For example, the tile class is going to be very challenging to display a tile, a grid of tiles on the screen properly, to snap your game objects to the tiles and all that kind of stuff. What we're talking about here is a division scheme for pathfinding. There are many different types of division schemes, but we find that using some kind of grid, a grid type of division scheme, is the easiest to learn from. Okay, so that's why we're giving it to you. All right, so again, please, kind of make sure you attend and work towards your assignment 2 by attending your labs. All right, so again, so this week and next week, they're worth together 4% of your final grade for the lab structure itself. Okay. Any questions before we begin? Questions, comments, concerns? Please bring them up now. I want to kind of finish off our housekeeping for today and move on to the lecture. Okay, hopefully you guys are good. And again, I just want to make sure you guys are also happy and understanding what's happening, right? The idea for everyone here is for you guys to become awesome programmers at the end of these 3 years together, right? And not just awesome programmers, but really understand what's required to develop games. There's a lot. Game development is a multidisciplinary field in kind of one aspect of computer science, if you will. But it also includes art, creativity, and it requires you to persevere, have a strong willpower, right? Because it's, when we start learning stuff, it's easy to quit. It's hard to continue. And anything good that we do in life typically is hard. Let's continue. All right, so let's talk about pathfinding today. This is our new topic for this week, and we're entering another module. This would be kind of the module for pathfinding. And the modules, when I say module, it kind of corresponds with what we're doing with our assignment. So assignment 1 was all around steering behaviors. How do we move, right, an autonomous agent? Assignment 2, and starting today, it's all around pathfinding. How do I move my autonomous agents with efficiency? Okay, that's a different thing. And sometimes what we talked about when combining steering behaviors is thinking about how do I solve problems with just steering behaviors. It's tough. But if we add pathfinding, then we actually have more dynamic movement for autonomous agents as they move around your game world, which is how they discover it, how they interact with it, and how they provide players with a continuous challenge, right, so that they keep coming back to play your game. Okay, so to improve replayability and interest, right? I mean, if the game is really not challenging, we don't want to play it. And what autonomous agents do is they increase our immersion in the game. We can feel that we're present when we're fighting, almost getting into a state of flow. We'll talk about that at some point during our time together at George Brown as well, which is psychological. We get into the state of flow, and we lose ourselves in playing the game. When an autonomous agent doesn't respond properly or doesn't look right, it breaks immersion for us, right? As an example, because we look at an autonomous agent, we're like, that's janky. That's not right. That's terrible, right? And we don't want that to happen. But to get it to that point, it takes time, and it takes understanding of how to manipulate your code and also use good judgment, develop good judgment, what looks good, right? And some of that comes from playing games and understanding what they've done and saying, hey, I want to make my enemy move just like that. I want to make my enemy, kind of react just like that. I want to make my enemy make decisions just like that. How do I do that? And those are great questions to add. All right, so when it comes to autonomous characters moving around, we want them to go to point A, from point A to point B. And sometimes, as an example, we want them to find the best route to a particular location. We have a starting location, and we want them to go to an ending location somehow. We would want them to be very efficient when they get there. A note about pathfinding before we begin. If you do it wrong, pathfinding can be really unfair for the player, because the autonomous agent will have inherent knowledge about the game world that the player will not have. And what that means is that the autonomous agent somehow, magically, will know the exact location of the goal, whereas the player, of course, does not. They only see what you allow them to see, right? And that's okay, but keep in mind that it becomes less realistic if the autonomous agent always unerringly finds the player, right, and uses the best path every single time, compared to some kind of variation. We'll talk about that as we go forward with other things in the second half of semester. All right, so let's talk about pathfinding and where it belongs. It belongs between decision making and movement. So, as an example, we have some movement. We've been talking about steering behaviors, and we haven't talked about decision making yet, because all we're doing for decision making at this point is raycasting at the best case. Maybe some kind of line of sight is what we're using to determine that there is a clear path ahead. That's the best we can do so far, because we haven't learned anything else other than how to move. And so pathfinding is kind of a middle step between decision making and movement. It allows us to move in a more efficient way, and we can, again, combine it with steering behaviors to make it really nice. So again, it's always around where I need to move exactly, as opposed to, kind of pointing in the right direction and hopefully you'll get there, right? So one of the things that happens is once the algorithm, any algorithm that you use, and an algorithm just a set of steps, programming steps, once it figures out what the target location is and it figures out how to get there, right, at the end of the day, it just takes over the autonomous agent and makes it move there. That's just it. That's how it works. And again, we're just talking about pathfinding and it's in isolation. We're not talking about pathfinding combined with something else. In order for us to understand pathfinding, we need to talk about graphs. And I know this is mathy, and I apologize, but it's part of what we need to do here. So again, there's two primary algorithms we're going to be looking at today, like we talked about earlier. One is Dijkstras algorithm, and the other one is Astar. And what they do is they use directed, non-negative, weighted graph data structures. That's what they do, okay? And so what is a graph? A graph is a series of nodes, like you see here, and edges, which are connections between nodes, right? Simple and straightforward, right? You can see here that at this part of the graph, this node right here, and let's just zoom in to talk about it. So the node right here, we can see that this node only has two connections, to the node above and to the node below. But it doesn't say anything, we know nothing from this node on how to get to this node, this node, this node, or this node. One thing to note is that pathfinding algorithms are very short-sighted, right, for the most part, when they first start off, okay? And what that means is most nodes, when we use pathfinding, can only see their neighbors. That's it. They don't see here, 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 and all the way down there. We don't have an idea of what that is. All we can look at is from one node to the other neighbor nodes, okay? So a graph that's non-directed means that it doesn't matter. All the edges are equally weighted, and they're bidirectional. Okay, that's an unweighted graph. Weighted graphs, on the other hand, are a little bit different, right? Weighted graphs are named that way because they have a weight number, a value between the two nodes. So example, if we take that same graph from above and add numbers to it, now it becomes a weighted graph, right? And these weighted graphs, what they have is, for example, if I want to move from this node to this node, the upper node here, it's got a weight of 1. So maybe when it comes to walking, if I was going to walk an autonomous agent from here to here, that's the cost of going there. Whereas if I go down this way, then the cost is only 0.6. Okay, so that's an example of weighted graphs. Okay, and we can also suggest that, let's say if I look at another example over here, if I'm going to go from A to C and I want to have the cheapest route, if you will, right, then I can add up the numbers. Typically that's what we do with weighted graphs. So if I go from A to B, the cost is 4. If I go to A to D, the cost is 5. So when I'm at A, chances are most algorithms are going to go to the cheapest, path, or the cheapest route, which is 4 from A to B. And then when I'm at B, I do another check. What's the cheapest route? Well, from B to C, that's where I want to go. That's 5. From B to D, I don't see C there, and that's 6. And chances are the right path is for me to go from B to C. So the total path length is 4 plus 5, which is 9 points, whatever that means. It could be 9 hours. It could be 9 units of some kind of distance, okay? But that's what it means. If I went the other way, if I went from A to D to B to C, right, because that's what would happen, that path length is 11 and 5, which is 16, much greater than this path, right? So we always want to take the shortest path. However, one thing to note, and I want to mention this to you now before we move into other more complex structures, is just because the path is the shortest for the autonomous agent to get there doesn't mean the path is the best. And what I mean by that is, what if the autonomous agent, we're going to be talking about this in the second half of semester, has a different goal? Like example, along this path down here, right? Maybe at D, the autonomous agent can pick up a health potion and heal themselves after taking damage. Then maybe A to D to B to C takes longer, but when they get to C, they're healthier. which is a better goal overall. Again, we're going to be talking about goal-oriented behavior in the second half of semester. All right, so weighted graphs are great because for rooms that are connected, we can kind of look and see how to get from one part of the room into the other. And you can see that we can overlay a weighted graph or on top of a level structure, which is pretty cool, right? Other types of graphs. Let's talk about other types of graphs. Directed graphs. So directed graphs look like they have an arrow or a vector, right, for each of the connections. Okay? So remember, a vector it represents both distance and direction. Distance could represent the weight. Direction, of course, is where the vector is pointing to, right? But here, when we look at this directed graph, and it's a directed weighted graph, both directed and weighted. You can have a directed graph that's not weighted, right? And a directed graph has arrows that basically tell you which way you can go, directions that you can go in. Some of these times, these arrows are non-bidirectional. They're only unidirectional, which means going from this node here, as an example, to this upper node, there's no way back with this kind of directed graph, right? Same thing if I go from this node, the starting node, let's say this is the starting node over here. So let me just draw that node, right? So let's say we say that, our starting node is way over here. This is what we're saying. So this is our starting node. And we want to go from here to here or from here to here to find the shortest point. Let's suppose, we have an ending node, and this is our ending node right here again. So let's just draw that one. This is our ending node. So we have our start node and we have our end node. We want to go and find that place. Well, let's see if we can get there. So we can go in two ways, here or here, right, as an example. And again, what we can do is we can map to the next smallest node. So here's a route we can take, right? So we go to this route next. So from here to here. And then we have to sit there and say, well, I can't go this way. And by the way, there's no cost associated for whatever reason here. That was missed in the diagram. But let's suppose even if I wanted to go this way, I cannot, right? There is no connection from here to here or back. Can't go back. Can't backtrack. But I can go from here to here. I don't know what the cost is for that. But let's suppose it's higher cost than 1.5 or 0.6. It looks to me that the next path here is this one. And then from here to the goal node, right? So start node into some kind of adjacent members and then to the goal node. What about if this length here, from here to here, was equidistant, so the same length? Then you could have an alternative path that allows you to go here or here, right? And that is also possible in a lot of times. How do you determine which of these two paths, if they're the same length, let's suppose, they're both 0.6, right? How do you determine which one to take? Your algorithm would have a default state where you decide, I always go with the right path. Example would be when we play Dungeons and Dragons, we say right, never wrong, right? So maybe that's your way of doing it, right? Or maybe you might say that, we are random. We just take a random path, left or right. Just make a roll the dice, and say which way we go because they're the same distance. One thing we don't know is what's happening at the next step. For example, if I go here and it's the same distance from here to here and from here to here, when I'm here, actually, like I said, pathfinding is short-sighted. So actually, if this was the same distance as this path from this point to this point to this point to here is actually shorter than from this point to this point to this point to there, right? And what we would do with most algorithms is explore both paths, both possible paths. Okay. So again, these are pretty simple examples, and hopefully you're getting it. But the idea of directed weighted graphs are the way what we do when we use pathfinding in any way. All right, a lot of times. Sometimes the path is two-way, but most of the time it looks something like this when we represent it in a graph. Okay. Questions so far before we move on? All right, let's move on. Dijkstra's algorithm. So there's this dude. He was a Dutch mathematician and computer scientist, right? Again, born in 1930. He got his PhD in computer science, if I'm not wrong. And what he did was he devised this algorithm he named after himself called Dijkstras Algorithm in 1956. And what it did, and it was widely accepted, it wasn't meant for games, but rather to find the shortest path in between nodes in a graph. That's what it was for. Okay, so he's a famous guy for a lot of other reasons, not just for pathfinding, but also he created all kinds of structures in data science and everything else. So really a pioneer in a lot of ways. And we would think about him in some ways as the father of pathfinding, modern pathfinding, with when it comes to how we do pathfinding in games. Okay, so what does Dijkstra's algorithm do? Well, it uses a start and goal node, right, with weights, and basically calculates the shortest path. So if you notice in this particular weighted graph, where all the weights are equal, it doesn't matter which path you take. There's multiple paths that will take you to get to the goal node, right? Is he? That's awesome, Nicholas. That's awesome. So when it starts off, if you go from the start to the goal node, right, as an example, then you see that there are many paths to get to the same thing. An example, let's just start drawing some of them to give you a sense of how that works. So you can see what I'm saying. I could go from here to here, and 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 from here to here. And that path, again, has 1, 2, 3, 4, 5 connections. And so the total path cost is 5. But even if I went this way, you know, so 1, 2, 3, 4, 5, it wouldn't matter. That's another path. Or this way, right? Or you could have gone this way, right? And you can see that there's a ton of paths here. Again, as long as you're moving towards your goal, many different paths. So this is one way of thinking about it. And that's great. But the idea here is, and I'm just going to clear my annotations here for a second. The idea here is that you want to do something that looks like this. You want to determine, kind of start off with when you're at the start node, and you want to get to the goal node, and you start evaluating each of your neighbors, right, to try and figure out the shortest path based on something called the cost so far. What is the cost so far? And that's what you kind of add up in terms of figuring out what the shortest path is. So here, if I'm going to go from here to go to from A to B, this is the idea. You would start thinking about what's the shortest path. Is 7 shorter than 9? Is 9 shorter than 14? Which one is the shortest? Well, it's clear that 7 is the shortest path. From 1 to 2 is the shortest path. Okay, what about from 2? Well, if I'm going to go here, what's the shortest path? Well, I can't go back, but I could go either 10 or 15. Well, it's clear that if I go to the third node here, example, then that is the next path. I know it's kind of hard to see with this one. Okay, just going to bring it in a little closer so you can see it. So again, from 2 to 3, because 3 has a total cost of 10, and 2 to 4 has a cost of 15, right, as an example. So that's obviously not the way we want to go. We want to go this way. So we go from 1 to 2 to 3. And now from here, if I was going to determine which is the next path, right, then from 3 to 4 actually is 11 points, where from 3 to 6 is actually only 2 points. So we go from 1 to 2 to 3 to 6, and then finally to 5. And that would be the shortest path, right? However, one thing that Dijkstra's algorithm does is it explores all paths. It explores all paths. So that's something that you want to consider as well. So it'll keep on exploring everything. And we'll talk about how Dijkstra's algorithm expands and what that means to expand. So node processing. How does Dijkstra do node processing? Well, what it does is it spreads out from the start node along each connection. So it kind of explores all the connections. It keeps a record of its source, which is kind of its the place where it started, its goal or its start. And once it reaches its goal, it can follow the path back to the start node along the path that it marched. So it kind of keeps track of each of the paths in a kind of a linked list. That's what it kind of does, right? And then what you can do is you can just backtrack and go from what path you found all the way back, add up the numbers, and then you have a cost for the path, right? And what you want to do is explore all the paths and see what the cost is for those paths. So it expands and it finds maybe multiple paths that are the same cost. Okay, and it tries to find some paths that are, example, undoable. So that's how node processing is done. Okay, so let's start over here. If we're going from our current node, node A, and again, I want to go to the next possible node. I have 1, 2, 3 nodes. As an example, I can go to there. It's a directed graph. You can see that there's arrows, and it's also a weighted graph. And let's suppose I have some kind of estimate, of the length of each of the connections. For example, here, connection number 1 is only costs 1.3. Connection number 2 costs 1.6, and connection number 3 costs 3.3. Obviously, it looks like the cheapest path is from A to B, right? So the cost so far is 1.3, right? And then if I was to take it further, node processing, if I'm going to go from B, I'm not going to backtrack. I've already explored these other ones, right? And I'm going to go from B, and I look at the cost to go from B to E, and the cost to go from B to F, right? From B to E is 1.5, and from B to F is 1.9. So it looks like when I add up the total cost so far, I want to go here from B to E, where the total cost, you add up those two, 1.5 plus 1.3, for a total of 2.8. Pretty simple. And we can keep taking it further, right, to see what it costs to get there. But however, let's suppose, we had another situation here, right, where we have a node C, which we didn't have before, and there was a way back. I mean, you can get into this way of figuring out the lists. And so what it does is, Dijkstra's algorithm uses, similar to what we're going to see with Astar, a lot of times the implementation uses 2 lists, something called an open list and a closed list, okay? And the open list holds all the nodes that have been seen, okay? So things that you've already kind of gone through. And the closed list holds all the nodes that have been processed. And process means we've seen them and we figured out that we don't want to use them anymore, or we've already used them, okay? So that's interesting. So again, let's suppose this is the goal node. Let's take it further for node processing. We start off at A, then we can start thinking about the 3 different costs, to get there, 3.3, 1.6, and 1.3. It's clear that we're going to go from A to B. And then from here, we can see 1.5 and 1.9, but we are going to explore E, but we're going to realize that there's no path to get to G, the goal node, and go back. And then that's not a viable path. Now we go back to A and we go, okay, we're going to go from A to B, and from B, can we explore F? We go to F, and we can clearly see that there's a cost to go to G, which is our goal node. Stop. Let's terminate our algorithm. Okay, so the final path is from A to B to F to G. Okay. So I also put Dijkstra's algorithm here in a step-by-step format. One thing to notice is that in this, this is kind of like pseudocode. People have talked about, hey, I want to do pseudocode, and that's pretty cool. Well, here's some pseudocode for you. Let's read it a little bit together. So again, we start with the node at which we are starting. We're going to call this the initial node or the start node. Dijkstra's algorithm will initially start with infinite distances. So what do you think we start with infinite distances, guys? Let's think about this for a second. What am I really trying to do? I'm trying to find the minimum distance, right? Whenever I do a minimal check or a min-max kind of check, right? Then if I'm doing a minimum, if I start out with an infinite distance, so positive infinity, right? Then anything is less than that. If you think about it, right? If I start off with positive infinity when I do my min-max check, then if I find any value, it's going to be less than positive infinity, right? So we start with infinite distances. And then we mark all nodes on the graph. Every node, we load them all up into the unvisited list. Okay, so we can start off on a visited list or an unvisited list. Okay, those are another way of doing things. So if all unvisited nodes, they're all marked, as unvisited first. So there's two states, visited or unvisited, we have here right now. And we create a set of all unvisited nodes called the unvisited set or the unvisited list. Okay, those are all the things. So we can put all the nodes in one big bucket, basically. We assign to every node some kind of distance value, a tentative distance value. We're going to set it to 0 for our initial node. So that's our start node. Our start node we set to 0 distance. Okay, and to infinity for all the other nodes. All the other nodes are infinite distance away. And then what we want to do is we set the start node as the current node. So that's the current node. Current node and the start node are the same at the beginning. So that's kind of the first two steps. And then for the current node, we consider all of its unvisited neighbors. Now, I'll be honest with you, a lot of times what we have is we have 8 neighbors, right? If we're using a grid system, which is what we're doing, we're using a division scheme for our pathfinding. A lot of times if I use a graph of any kind, some kind of grid, we have 8 neighbors, right? We have up, down, left, right, and we have top right, top left, bottom right, bottom left, right? Those are all the 8 neighbors. For your assignment 2, you've been asked to only consider up, down, right, and left, and not to consider any of the diagonals, okay? So unvisited neighbors, if you're using Dijkstra's algorithm inside of our, for A2, assignment 2, they do not consider diagonals as connected. Imagine that you don't have any lines at all, no connections between your diagonal neighbors. Okay, and we want to calculate their distances through the current node. So what is the distance between, the current node and the other nodes? Okay, and then what we're going to do is compare the newly calculated total tentative distance to the current assigned value. So whatever the current assigned value is, we keep track of the cost so far. That's what that means, and we assign the smallest one, the smaller one, the distance. Now here's something. How do I get this tentative distance, right, from where we are to the next node? Well, we know it's infinite, right? So we start thinking about, again, if all the paths were equally weighted, which is what we talked about earlier up here, if all the paths are equally weighted, right, then initially every node is equally good, right, when we start off. We don't have a node that's smaller. So we start exploring all of them, guys, all of them. So we say that, okay, fine, we choose the smallest one, but that could be any random node. But if we're doing a right way winding, we start off, let's say, with the top node, right? Again, if we draw our neighbors, if we're using Dijkstra's algorithm here for a second, and if I start drawing some lines, I have, let's say, for example, the top, I have the right, I have the bottom, right, and I have, left, and I'm here in this node, right, and let's suppose they're equally weighted, all of them are worth 1, as an example, then I could start with this one, start with the top. And typically what I normally do is I do this right way winding idea, right, where I start off with the top node, and I use that just as a standard, right, as an example. It's not really something that you need to do, but I do it because I want to have some method, right? I want to use some method for me to be able to traverse from one path to one node to the next node. So start with the top. Okay, now when I'm here, now this is the current node. Okay, once I moved away, if this is where I was and I'm here, now I've accumulated whatever the distance is here. Let's add 1, right? So I'm here. I have a total cost, path cost of 1. And I just keep going up, and I'll keep going up until I'm not able to go up anymore. There's no more neighbor nodes that is up, and I only have these neighbor nodes left. If I'm starting on the bottom left corner, I may not have a left or a down option, which means I can only go up or right. And what I would normally do is go all the way up to the top, and then I would go all the way to the right. That's what I would do, and then until I again, I figured out the cost of whatever that cost is. And I would just keep on marking up the cost, 1, 1, 1, 1, 1, all the way, and to figure it out, okay? Okay, so that's how it works. And then when we are done considering all of the unvisited neighbors, right? So we've done doing all of these. We want to follow all the paths here or here or here or here. As an example, anything that's viable, all unvisited viable neighbors, right, of the current node, mark the current node, this one here, as visited, and go to the next node and remove it from the unvisited set. So now clearly we're not going to be back in the goal node. If this was the original goal node, as an example, when we're marching along, so right here, this is the start node, I should say. So if this is the start node, right, there it is, then the start node would be inside of it would be removed, right, from the unvisited set because we've already visited the start node, right, and we've moved here. When we move here, we take this new node away from the unvisited set and put it inside of, we'll just remove it, right? Visited node will never be checked again. That's one thing to note. So if I go through this thing, if I've gone through those nodes, I'm never going to check those nodes again. Somehow, when I go through the algorithm, if the destination node goal has been marked visited, or this is the termination condition, or if the smallest tentative distance among the nodes in the unvisited set is infinity, smallest node, the smallest set is infinity. That means there's no. And how do I get infinity? If, for example, I'm in a corner, right, and there's no place to go. I don't have another node that I haven't visited, right? If I don't have any nodes that I haven't visited, right? If I am in a corner and I've visited all the other nodes, right, as an example, and or if I found the goal node, then terminate the algorithm, because either I found a way to get there or I found the goal node. If I found a way to the goal node, or if I'm in a corner somewhere, and there's no way I can get out, or there's no path. All right, so this is kind of a simple algorithm, but I mean, again, it can have its complexities, and that's why we're talking about it. And finally, otherwise, select the unvisited node that is marked with the smallest tentative distance, set it as the new current node, and go back to step 3, which means for the current node, do it again. So loop. It loops back in here again. Okay. Here's a pseudocode for that. All right. So again, you can see that in this case, we have a function called Dijkstra, right? And we have a graph in a source. And the graph itself is a series of vertices, right? And for every vertex in vertices, think about the vertex as each point in the graph. Then what we do is we loop through each of them. That's a for each loop. And we set the distance for that particular vertex to infinity. And we also set the previous node when we start off as undefined, right? And then we add v to q, where q is a set of vertices that we're checking out, right? And what we say is the distance from the source, which is the start, is 0. So this is kind of our setup. We set this up. This is kind of like our initialization, right? We initialize everything like this. So we have basically for each node, for each vertex, which is a node, we have 2 properties really. We have the distance and previous, okay? So we don't have a previous and we don't have a distance. We set the distance to infinity, right? And the previous to undefined. So now while Q is not empty, for every vertex in the list, in the graph, that's what Q is, right? For every vertex in the graph, what we want to do is U, as an example, is the vertex in Q with the minimum distance U, whatever that minimum distance is. So you're going to choose a vertex with the minimum distance. And what we're going to do is when we find that vertex, remove that from Q, from the vertex set, right? And now for each neighbor V of U, still in Q, whatever's still inside there, well, we can check the ones that are still in the set we want to check, which is the open list. That's what this is. What we want to do is we want to calculate what's the next one to go to. And notice that it says here in this little piece right now, right? We're going to, we have a return. We have the distance and the previous list, an array of distances and an array of previous nodes. That's what we're going to return out of Dijkstra. A lot of times I got to mention that pathfinding algorithms are recursive. Okay, you guys should know what recursive means. That means that the pathfinding algorithm calls itself a lot of times. How does this thing work? Well, it kind of grows and looks something that looks like this. So it kind of grows up, and And it keeps on searching every node, every node, every node. And you can see the blue nodes are the ones that have not been visited yet as it continues. If it finds things like impassable blocks, those are not considered, those nodes in the list are not considered and removed, right? So they're not something that they consider. And you can see that the red nodes are marked as completely visited. And as the green nodes continue, they get closer and closer to the goal. And then finally, when they get to the goal, you have the shortest path. Okay, that's how it goes. Pretty straightforward. Now, notice what it does. Look at the coverage. All right. So what it does, and it does it almost instantly. It doesn't do it instantly. It takes time for the biggest. And again, this is like full coverage amount of nodes. If you have to consider this thing, right? Imagine if you have enough nodes to cover the entire, game world. That's what this is, if there was that many, right? But you may have less than this. This is very dense, a very dense graph. So obviously it's going to take a long time to do. But if you had less, if this was less dense, and you created nodes that were less dense than this, you could theoretically, use Dijkstra and be very efficient to find stuff. However, it will explore every single path to find the shortest route. So that's Dijkstra. And Dijkstra's algorithm illustrated in a shorter form. You have the start goal. It starts exploring, nodes around the start, and as it grows, it expands. This is the expansion idea. Again, it keeps on expanding and exploring all kinds of, all the nodes. And it explores on this side and explores on this side. You can see that it found a shortest path, right? And it keeps on exploring, in this side until these nodes here. Okay, so I just want to mention this. This is where it can kind of be a little bit more efficient depending on how you allocate things. Notice there's some nodes here like this one, right? Like this one, like this one, like this one. These nodes here that are gray, okay? These paths here, it kind of starts looking at these nodes that are the farthest out. Do they have a greater cost than the path that we found to go to the goal node? If so, stop, terminate. We don't go and check these ones or these ones or these ones because we've already found a shortest path. Anything beyond here is too long. Anything beyond here is too long. Anything back this way is too long. Anything down this way is too long. So these are areas that are unexplored because we've already found a viable path that's shorter than anything else over here. Make sense? Okay. Again, this is just illustrations so you understand how Dijkstras work. All right, questions so far before we continue? How about comments? What are your thoughts? Do you think this is an efficient algorithm? Would you use an algorithm like this in a game? Simon says it was crazy. Simon, what do you think? Do you think you would use an algorithm like Dijkstra's in a game? Lucas says, I would. Okay. And Simon says, depends on the game. Again, I think I agree with the depends statement. Depends is always a good answer. And the reason why is depends on what you want to do. If you want to use Dijkstra, and let's suppose you're not just going to the goal, but you have a separate secondary goal, right? And the secondary goal is picking up items, right? Then you want to be able to, and you want to explore the world, then Dijkstra is a good choice because then you can satisfy both the main goal and secondary goals, okay? But if you want to get to the place fastest, then sometimes, and most of the times, Dijkstra is not the fastest or most efficient algorithm. It covers the most, but it doesn't, it's not the most efficient. One thing we have to talk about is we've been talking about graphs, and what do we do with graphs? How do we represent them in C++? Because this is something that, we talked about how to do it. It looks nice, but how do I represent these things? A lot of times we use something called an adjacency list, okay, which is kind of cool. This is like different than a grid. We were going to ask you to make a grid of tiles, right? But what we're doing here is just using an adjacency list. So what this represents is a graph as an array of linked lists. An array of linked lists, okay? And the index of the array represents a vertex, and each element in its linked list represents the other vertices that form an edge with that vertex. So example, here is the class graph, right? And it has an integer property of a number of vertices, right? Number of vertices would be nodes here. we have a linked list. So a list in C++, we've just mentioned it like this, STL list, which is a collection, which is a linked list of type integers, right? And we can call this the adjacency list. So it's a list of linked lists, an array of linked lists, basically what this is. And then what we're going to do is we have a constructor function, which is graph, where we take in the number of vertices. And what we can do is we can have another method called add edge. And the add edge method takes two things, a source and a destination, right? And it has the source as one of the vertices in the list, and the destination as another vertex in the list, and that is the edge that it adds. So I can construct my graph by using the add edge method. So notice if I take in source and destination, here we can be even clearer. We can also take in something else, which is the vector of integers, right? And we can call this, a vector of integer, and it's an array of vector integers. That's what we're saying, right? Which is called the adjacency list. That's what it is. This is what this is, an adjacency list. And what we want to do is we have two things, a source and destination. And what we want to say is for that particular source node in the adjacency list, push back the destination, right? So we make an edge there. And for the destination, push back the source, right? So we kind of add those two things into the adjacency list for those two things. Again, it's very interesting. And then what we do is we print the graph, right, using an adjacency list, where we can output each member of the graph. Okay, so very interesting. So a couple of different structures, and it's very common to use an adjacency list to represent a graph structure. Yes, it is Raul. How about Astar? So Astar, we talked about Dijkstra, and we said that it explores a lot of stuff. But what about Astar? And Astar is probably one of the most popular search algorithms you're going to hear about, and it's used extensively everywhere. Let's talk about what it is. It was made by these three gentlemen, Peter Hart, Nils Nielsen, and Bertram Raphael of Stanford Research Institute, or SRI. And they first published their algorithm just a few years after Dijkstra did in 1968. And it always is looked at as an extension of Dijkstra's algorithm. And what it does is it performs better because it uses something called heuristics as a guide to its search algorithm. Okay? And it's designed more for point-to-point pathfinding compared to exploration. If I want to explore the world, Dijkstra. If I want to do point-to-point, Astar or something like it. Okay, and there's different variations of Astar we're going to explore in future lectures. We're also going to have some kind of an estimated total cost value, which is the sum of the cost so far and some kind of heuristic. That's what's going to be at every point in the path. Okay, and we'll talk about what heuristics are in a bit. So one thing to note is Astar is something called an informed search algorithm. So it knows stuff. It has a little bit more foresight, if you will. And it also is also called a best first search algorithm. Okay, best first search. And the way it does is it uses weighted graphs. Starting from a start node of a graph, it aims to find a path to a given goal node having the smallest cost. Okay? And it does this by maintaining a tree of paths originating. So think about that. It's a tree compared to some kind of adjacency list, right? So a tree data structure originating at the start node and extending those paths one edge at a time until its termination criterion is satisfied. So that means if I find a path to the goal node, I'm done. I stop. Well, and you're might say something like, well, wait. If that's what it does, well, does it perform better than Dijkstra? It's better than Dijkstra in terms of performance, fast, right? But isn't as thorough as Dijkstra? And can also meet things like secondary goals like Dijkstra can? The answer is maybe not. And we got to consider that, right? So here's part of it. Each iteration of its main loop, A star needs to determine which of its paths to extend. So which where do I go? Do I go to the top neighbor, the right neighbor, the bottom neighbor, the left neighbor? Where do I go? And what it does is it minimizes the function n. So we look at a function that looks like this. Okay, I know math. I'm sorry, guys. I'm talking about math again, but here it is. We can say that we read this as this. F at n is equal to g at n plus h at n. Right, where f at n is the cost function, g at n is some kind of value for the cost so far. So what is the cost so far? Plus h at n, which is the a heuristic function, an estimation value of are we getting closer or not. That's what h at n is. That's why in many ways, if we think about it, the heuristic term, which is where we can tweak our program, this part right here, this can make all the difference in finding the shortest path, because g at n, like it says, is the cost of the path from the start node to wherever we are right now. That's the cost so far. That's what that is, cost so far. Where at h and n is some kind of estimation function. And why estimation compared to knowing? Well, because we don't know exactly how far it is. Before, we had no estimation function in Dijkstra. Every path, we just kind of process each node as it comes, and we add it to the total cost, and then we can explore all the nodes. We're going to explore everything, the entire game world. It's going to take longer, okay? More thorough. But this uses a heuristic function, and whenever we hear the word heuristic, it's a fancy word, and people get all upset. They're like, oh, heuristic, I don't know why we're using these words. Because it means, think about it as an estimated value. Okay, that's what it is. So really what it is, A star terminates then when the path it chooses to extend is a path from the start to the goal. So we found an extension that takes us to the goal, or if there are no paths eligible to be extended. If I have no place to go, terminate. Okay, that's how it goes. The heuristic function then is a problem-specific function to be discussed in a couple of slides. So what does this look like? It kind of looks like this. So it starts plotting out the path one step at a time. It does explore the game world, but what it does is it does it in a more systematic way, right? Similar to what Dijkstra does, but you can see that it finds that once it finds the path, it stops. It doesn't explore all up here or down here. It doesn't explore everything. So you can see in this particular case, it works faster than it would have worked if we were using Dijkstra. Okay, that's how it works. All right, let's talk about the pseudocode for the algorithm. Let's set the setup. So the setup, when we set up the pseudocode, we look at the node goal as the start goal, as the goal, and the source node is denoted by node start. We have two lists, the open list and the closed list. The open list consists of all nodes that have been visited. We talked about this again, but not expanded, meaning that the successors, so the next nodes, have not been explored yet. And this is the list of pending tasks. So think about this as like things we need to do. That's in the open list, things we need to explore. Closed list consists of nodes that have been visited and expanded, which means I've also looked at all their neighbors and their neighbors and their neighbors' neighbors. Okay? That's expanded. That's what it means. Okay, so that's what goes into the closed list. Okay, and this is explored already and included in the open list. If they're included in the open list, then we can explore them. If they're in the closed list already, we don't touch them. Right? Here's the algorithm. I'm not going to go through it, but I've actually included here it for you in on the PowerPoint slide. But basically, what it does is exactly what we said. Okay, so I'm just going to leave it here for your pleasant reading. It's there for you. This is in pseudocode, and you can take this algorithm actually and create code from this if you really wanted to. Let's talk about A-star node processing a little bit. So we start off here again, and now we have two things. We have a heuristic function, an estimation, plus a cost so far. So we have two properties instead of just one. Okay, and so we look at, for example, what is it from us to go from A to B? Well, the cost to traverse from A to B is 1.3, but the heuristic might be 3.2. That's the distance to the goal node, the approximate distance or the estimation from B to the goal node, right? So in terms of total cost then, what we do is we add up 3.2 plus 1.3 for B, and the total estimated cost just to go to B is 4.5. For us to go to C, it's 1.1 for the cost so far, plus the heuristic value is an estimation from C to G, and it adds those two values together to come with an estimated total cost of 4.8. So clearly, from us to go from A to C is more expensive than for us to go from A to B, even though the cost so far in the interim is actually smaller for us to go from A to C. But we're being informed by the heuristic evaluation function that's pointing us to go to B first. Okay? So Raul says, you need to know the end position of A. Yes, we kind of need to know approximately where the direction of A is, of the goal, for us to use A star. And that's what the estimation function is. We're going to talk about what that estimation function is. Okay, so again, if I'm here, you can see that if I'm at B, because we chose B, because that's the shortest one, it's only 4.5 compared to 4.8. We have two values to add up. Now we look at D, which is 5.6, and E, which is 4.6. So clearly we're going to go from A to B to E to G, and that's the path that we're going to take. Node processing. Again, it talks about that a little bit here. Data structures. Again, some possible data structures that we use are priority queues, not shown. Okay. We also use some kind of heaps. We can also use a bucketed priority queue at the bottom. This is what a priority queue would look like, right? As well as a tree representation. And notice that the tree representation that we have here is a binary search tree, right? In many ways, it would be a binary search tree if the stuff on the left. Actually, let me take that back. So this looks like a binary tree because a binary tree has a node, and it has a left node and a right node. Every node itself has either a left node and a right node, or no nodes. Okay, that's what it has. It normally does not have a single node, like a dangling node over here. It doesn't normally have that. So normally a binary tree, again, is equally weighted and equally, allocated, if you will. Okay? We can say that when we look at a tree structure, for those people who've never done algorithms and data structures, we can say that this part of the tree, right, is a subtree. That's what it is. This is a subtree. And this would be the left subtree. We can also say that this part is the right subtree. Okay? When we look at this subtree, we see that there is a root node. There's always a root node. So this is the root node of the entire tree. But for this subtree, this now becomes the root node. Right? Again, it lends itself well to recursion. And we can see that for this tree, this subtree, it also has another subtree right here. This is another subtree. And here's the right subtree. Okay, here's the right subtree. The right subtree really kind of only has one node, right? So we have subtrees, we have root nodes, and we have leaf nodes. Leaf nodes are the ones with no other nodes. These are all leaf nodes right here. 9, 10, and 5, those are all leaf nodes. So are 7 and 6. So 6, 7, 5, 10, and 9, those are leaf nodes. And this one and this one and this one would all be considered eventually root nodes, as well as child nodes. So these ones here are child nodes and root nodes. This is the main parent root node, right? It doesn't have any other predecessor. Okay. So trees are interesting in that they're very quick and efficient to use, right? And the algorithm to set them up isn't terrible. Okay, so tree representation is pretty cool. So this would be a binary tree. A binary search tree is an ordered tree where we build the tree where everything on the left of the root is less than the value of the root, and everything to the right of the root is greater than the value of the root. And it goes for every root. That case has to be the same for all of these values. So for example, if this original root value had a number, right? And let's say if I look at these values here, this number here would have to be greater than all of these, right? And less than all of these. Okay, so this is not a binary search tree or a BST because 2 is not greater than 3, 5, 4, 7, and 6. It's actually less than all of these. So this is not a binary search tree. If this value was greater than all these, but less than all of these, let's suppose, I don't know, I had a half value like 7.5. If this value was 7.5, then this first part would be we could start thinking about this as a BST. However, it has to be we have to apply the same rule to all of its subtrees. So for example, 3 would have to be greater than 4, 6, and 7, and less than 5. That's how it'd have to be organized. Okay, a BST, which is a binary search tree, is very efficient because we know that anything to the left is lesser than anything to the right. We can load up and we can use a tree structure for pathfinding, especially Astar, because we can load up the right side with things that are greater in terms of total path cost and things that are lesser over here. So literally we do a tree traversal on the left until we find the leftmost node, which is this one, and that would be the path. That would be the shortest path right here. Organizing, or up front, if we organize the binary search tree, if we had a binary search tree and organize it this way, right, as an example, then finding the shortest path would be very, very fast. Okay, and if there was one. Okay, so just giving you a sense of structures, data structures. All right, so what then is a heuristic function? Really, again, we talked about it, returning an estimated cost from the given node. So here's an example of a heuristic class, right? We have our goal node, whatever that is, and we want to define a function called heuristic, right? This would be the constructor function, and this, notice that this is using def. A lot of times when we see something like this is Python. Doesn't matter, it's just pseudocode for you, right? And the heuristic constructor takes a node, which is the goal node, right? And what we want to take is whatever the goal is, the current goal, right, for estimation, and we take the goal node minus that particular goal, and we get an estimate. That's how we calculate the estimate. Okay, it's pretty simple, but we'll talk about how this works in a little bit, and there's some suggestions we can use for making this better. So what we want to do, we talked about this already. We talked way up here about this function that we want to figure out. So the cost so far, or the total cost, is equal to the cost so far plus the heuristic evaluation function, whatever that is, right? Which is just an estimate of how to get there. So to find f then, that's why I'm going down here. What is f, right? Calculating f. What we want to do is we want to say that f, right, is equal to g plus h, right? G, again, is the movement cost in our grid. If we're going to use a grid system, because that's what we're going to do for assignment 2, G is the movement cost. How much does it cost to move from one part of the grid to the next one cell to the next cell? There's always a cost. Even if it's a cost of 1, right, it's a cost. And if it's a cost of 1 for all the tiles in a grid, then we can remove that cost. We can actually just not even consider it. If the cost is the same, right, for every single grid, every single tile in the grid, we can remove it because it's not important. If the cost is different, and a lot of times movement costs can be something like, hey, what if I'm walking on water, or walking across water? What if I've got difficult terrain? What if I'm walking inside of a cavern or rocky step? What if there's a path, like an actual road that's already there? Obviously, the road is going to be the cheapest way to go, but it may not be the shortest path to get to the goal, right? So we can adjust the grid to have a movement cost from one tile to the other tile based on what type of terrain you're on. Yes, it could be like Civ. And the H is the estimated movement cost to move from that given square on the grid to the final destination. Now, there's a couple ways to figure this out. Think about this as some kind of smart guess as to how to get there. So 2 types of heuristics are the most common. The first type of heuristic we're going to talk about is something called Euclidean distance, which in what we think about it is as the crow flies. All right, so it is measured directly between the 2 points in space through walls and obstructions. We don't even care about walls and obstructions. We just almost like, if I can target a line of sight from where I am right now to the goal, it's as the crow flies. I know that length, and a lot of times we use a square root We can, by the way, we can also use, instead of a square root function, we can use a, what we've talked about before, which is a squared distance function. Either way, there's some form of distance gathering, right? And what we say is, once we have that h, that is the distance, the Euclidean distance, right, in terms of pixels, from one part, the node that I'm on, to the final goal. That is the h value we can use, right? So when do we want to use this heuristic? When we are allowed to move in any direction. If I can move in any direction, this is a great heuristic to use. That means I can go diagonal. If I use this heuristic and I can't go diagonal, I'm not taking advantage of this heuristic. So what does it look like? So here's what the Euclidean distance looks like. Here's my start, and here's my goal node. Let's say it says assume the red spot. Oh, it's the other way around. The red spot is the source, or the start, and the green spot is the target. Then Euclidean distance is the distance from here to here, right? And remember how we figure this out? We take the total values of y, right? So 1, 2, 3, and you know, as an example, and the total values of x, 1, 2, 3, 4, 5, 6, 7, 8, right? We kind of add those up, and then we subtract all the y's from all the x's, or sorry, we add them up. So we say 3 times, we multiply them together. So 3 times 3 is 9, and then 8 times 8 is 64, and 9 and 64 we get the square root, and we come up with this, you know, Pythagorean distance or Euclidean distance from here to here. So, okay, let's do a little exercise. What is the Euclidean distance from this cell to this cell? Can someone help me out? Figure this out. Let's suppose, just to give some context, here, let's suppose that we consider that the top left cell is 0, 0. This is the top left cell. And we count this way and down, just like we normally do. All right, so what is the total distance, the Euclidean distance from here to here? First of all, what is this number? Right, that's what we have to calculate. So we say that if this is 0, this is 1, x is 1, 2, 3, 4, 5, 6, 7. So this is 7 on the x-axis and 1, 2, 3 on the y-axis. So 7 and 1. Let's put those numbers down too. Okay. Let's do that. So this is cell 7, 1. Y. 7, 1. Okay. Is 7, 1? Did I say 7, 1? 7, 3. I'll be okay. 7, 3. Okay. And so again, what are your thoughts? What are your thoughts about this? What is the Euclidean distance? So Rose says, okay, 7 to the power of 2, right? And 3 to the power of 2. And we take those, add them together, and get a square root. Okay, so let's see if that's true. So again, if I was to do that, and if I was to get a calculator out, let's do that calculator, so calc. And we can say that, we can start thinking about this, right? So we say that 7 to the power of 2 is 49, right? 49 plus 3 times 3 is 9, which is 9. So we have 58, and we want to take the square root of that, okay? So, which is this. And we look at that the total distance here is 7.61 pixels. 7.61 pixels. If these are pixels. Or 7.61 squares if these are tiles. Okay? 7.61 squares. So if I was starting with the heuristic function, which is Euclidean distance, 7.61 is where this one starts off, from here. All right? So I would write that down. So let's just write that in this example. So this is, the total would be 7.61, 7.61. And that's the heuristic function. So h is equal to whatever that value is. Okay? For this particular cell. For this cell right here. Okay. Let's see if we can figure out the distance from the other cells. All right. So what about from this cell? From cell 0, 1. Or sorry, 1, 0. Right? From 1, 0 to here. How do you figure that one out? We went from 0, 0. That was the easy one. What's the calculation we use now for the heuristic value of this cell? By the way, it's going to be the same value from here to here, or either one of these might be very similar, but we'll see if this value here is the same as this value here. Okay? So how do we figure this out? Well, it's 7, so the difference in x's, 7 minus 1 is 6 squared. So let's see if we can do that function. So 6 squared. So 6 times 6 is 36. And then again, we don't change 3. 3 minus 0 is still 3. So it's 9, right? So plus 9. Right? So it's 45. And we want to take the square root of 45. And now we get a value of 6.71. Let's say 6.71. Let's keep this calculator going. So we're going to come back to it. 6.71. So that is now the heuristic function of this one. I'm just going to do this small little thing, guys. I know it's tedious, but please bear with me so I can get you to understand. So this is 6.71. 6.71. And that's the heuristic estimation function that's calculated this next cell. This next cell is 6.71. How about this one? Okay, well, let's suppose this is the other way around. So now we're going to say that this cell is 0, 1, right? 0, 1 this way. 1, 0, and 0, 1 you might think it's the exact same. And let's see how that works. So again, is it the same value so far, right? So if we bring this back over, right, then we can do the same calculations. So 7 minus 0, you take the difference of x's. So that is 7, so it's 49, right? And then you take the difference in y's. 3 minus 1 is 2. 2 times 2 is 4. So we add 4 plus 4. We get a value of 53. 49 plus 53. We take the square root of that, and we get a value of 7.28, right? So now we can see clearly that when we come to this, that 7.28, my friends, is a higher value to go down. H is equal to 7.28 than it is to go across. Does that make sense? All right, so where would Astar take us with Euclidean distance? Here. This would be the next step. Because it's if all cells were equal cost to traverse, and all we cared about was the heuristic evaluation function, right? It would be either this or this. We're not considering this neighbor, right? Because this neighbor right here is something we're not considering. But in using Euclidean distance, let's also do this one, right? Because that's fair. So this one would be 1, 1. Okay, let's see what the distance here is for 1, 1. Maybe this is the next point that we want to go to if we're using Euclidean distance where we can use all the neighbors, right? Let's try and do one more. All right, so again, for 1, 1, we'll put that value down in here so because we can't fit it quite in there, right? So we'll do that. So again, for 1, 1, if this cell is 1, 1, then what is the Euclidean distance for this? Let's bring up that calculator again. All right, the Euclidean distance from here to there, from this cell, right? So we bring up our calculator and we do it one more time. So if we're going to use this thing, we're going to say that, okay, the difference in x's, 7 minus 1 is 6. 6 times 6 is 36, right? So that's 36. And the difference of y's, 3 minus 1 is 2. 2 times 2 is 4, plus 4, right? It gives us a total value of 40, and we take the square root. And so this distance, 6.32, is the heuristic evaluation function distance for this point. So if we took the diagonal into account, then this diagonal point would be the smallest cost of each of these three neighbors. This diagonal point right here, based on using Euclidean distance. Okay? 6.32. Questions around this? All right, so interesting algorithm. I like it, for heuristic distance. If we're using diagonals. In assignment 2, you are not to use diagonals, so Euclidean distance may not be the best formula to use, the best heuristic evaluation function. The way the fill pattern looks is just like this. So if, you can see that it finds, kind of the path, the lowest kind of the lowest cost based on Euclidean distance. Okay, what about another algorithm, Manhattan distance? This is the second algorithm that's very, very popular, right? And usually we have three approximation heuristics. I'm only going to be talking about two. Here is Manhattan distance. So let's take this away and just say let's just talk about Manhattan distance for now. Okay. So what is Manhattan distance? It's nothing but the sum of the absolute values of the differences in the x's and y's. Okay, so that's a different way of doing things, right? And why is it even called Manhattan distance? You can think of us going around a block. Manhattan is made up of many blocks, as an example, with buildings in the middle. And imagine if I'm going to go around using the streets in a grid-like pattern, right? But I cannot go diagonally. I can't cut through a whole block. I have to go around the building, right? That's where the term Manhattan came from, okay? So it's like Manhattan. You have to go around the buildings. You can't go through the buildings, right? So again, that's how you do it. When we want to use this heuristic, when we are allowed to move only in 4 directions, which is for your assignment 2, right, left, top, bottom. And we would do this in a different order if I was winding. And what does it look like? It looks like this, okay? This is the fill pattern. Okay, notice that it goes directly down to here, right? And it goes in a very strict method down to this point, okay? So the heuristic value looks like this. We take the absolute value of the x value of the node, the current node where we are, and the goal node where we're going to be. We take the absolute value of the difference, whatever the difference is, and we take the absolute value of the difference in y's, and then what we do is we add them together, right? And we have a value that we're going to use, okay? So that's the Manhattan distance. That's what we do. That's the heuristic value, the heuristic calculations for the Manhattan distance. So let's go back. So then if we were to consider Manhattan distance, then really what you're doing is it's like you're counting squares, right? So let's think about this. If this is do the same thing as we did last time. So we'll set up the goals and see which one is better. By the way, is this route here cheaper than this route here? This route cheaper than this route? What are your thoughts? Simon says the exact same. Absolutely. Why? Because it's equally viable, right? It's equally viable. Now, what about if, let's just make it more interesting, right? What about if we get to the point where, and this is what we're going to talk about in our scenarios. Let's do something to mess this up. We haven't done this so far, but let's suppose that there is a wall that goes like this, right? So how would Astar function with Manhattan distance heuristic based on this? Well, first of all, these two nodes would be the exact same. So we would try, let's suppose we do that right winding idea. So we start with the top, and then we go to the right, and then we go to the bottom, because they're all the same, right? In this case, this is the disadvantage of Manhattan, okay? So let's say, for example, I start marching. The first node I would check then, if I was doing it, would be from here to here. That would be the first node that I would check. Okay, now, which one is cheaper? From this one or this one? And this is where we can get some variation. Which one is cheaper? This one or this one? Okay. Well, let's see how this works if we're going to check these two things out, right? So if we had this scenario, and let's explore this scenario a little bit, right? And we're making these nodes. And if this, again, we assume that this one is, again, 0, 0. And we use the absolute values for all these things, right? Let's come up with some values for the heuristic function if all the grid cells, the traversal cost was the exact same. Okay, so they're all worth 1. We just discount them all. Here it's 1, 0. So 1, 0, and let's suppose the same thing. So this is, again, we're counting 1, 2, 3, and 1, 2, 3, 4, 5, 6, 7. So this, again, would be 7, 3. Again, just to set it up, this is the setup for us, so we know we're talking about apples and apples, right? So this is 7, 3, right? Okay, from this node, from the first node, what is the Manhattan distance from here to here for the first node? How do we figure that out? We got to figure out the first node too. We have to have a cost from here to here. How do we figure that out? Anyone want to try and guess? Remember, if we go up a step, it says that we use absolute value, right? We use the absolute value of the differences. So we say something like this. We say 7 minus x minus 0, that's 7, right? And 3 minus 0 is 3. So 7 plus 3, the Manhattan distance is 10. If you think about it, it's like counting squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's how we figure it out. It's counting squares, right? So this is a distance of 10. Let's put that value in there. Okay, so that's here. Okay. And what about this one? So if I was going to count from here, I would say, so I'm here now, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So this would be 9. We'll put that there. Okay. And what about this one? This would also be 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Whoa, wait. Sorry, from here. 2, 3. Yeah, same cost. 9. 9. All right, so 9, 9. So it's a different kind of fill pattern that you're going to see. Okay, cool. We got these two 9s. I'm putting them over here so you can see them. And what about this one? Well, this one would be probably 8, right? Because it's 1, 2, 3, 4, 5, 6, 7, 8. So this one would be 8. Pretty simple to figure out. And what about this one? So from here. So 1, 2, 3, 4, 5, 6, 7, 8. Same costs. Right? Let's fill them up. What about this one? 1, 2, 3, 4, 5, 6, 7. Okay. So we put the 7 in there. Obviously this is going to be 6. And this is going to be 7. And this is going to be 8. Take a look at the pattern, the fill pattern that's emerging. Right? This will be 7. 7. Right? This will be 6. This will be 5. Okay? This will be 4. 3, 2, and 1. And by the way, it would stretch as long here too. So if you want to say these are 2s, this is 1, these are 3s, right? And these are 4s, just to give you a sense of what this is, because you would have a grid space for all of these tiles. These are 5s, and these are 6s. So there we go. We've kind of allocated values for all of these tiles. These are nothing. And why are they nothing? They're impassable tiles. Let's allocate them with an I. Right? So we have impassable tiles for all of these. Or infinite. It's an infinite distance. Call it whatever you like. Positive infinity. Okay? Okay. I like it. I like it. So then if I go and march, let's march along now, and let's do this exercise. If I mark from here to here, and I go from here to here, that's the next one, because I'm doing a right winding order. There's no place up here. So we start at the top and go to the right. If this is the way we're traversing for our first path, and then we go down, right, because this one is infinite. I'm not going to go that way. And then I go down again, and down again, right? Because that is infinite on this side, right? And then I go to the right, and I keep going to the right, and I march to the right. And see how I'm marching? This is the way you're going to move your autonomous character until we get to here. And that is the first path. What is the path length for this first path, guys? You add up all the stuff, all the numbers. So 10 plus 9 plus 8 plus 7 plus 6 plus 5 plus 4, 3, 2, and 1. Okay? That's what it costs. All right, then we go down here, and we say, what about this path? If I was to go this way, this is the next viable path. Let's undo that change, and let's change the color. So this is path number 2. And let's make this yellow path. All right, so we say, well, we want to try and go this way. 8, it's the same, because we go back to this one, right? We go back to all the neighbors. We come back to this one. We say, all right, we went here, and now we explore this one. All right, cool. Can I explore this one? Well, this has been explored before, right? So since we've explored this path before, we go down, right? And what about this one? Well, we've explored this one, and it's the same cost as this one, so we go down here. And then we kind of add those ones. So we say, well, what's this cost? So it's 10, 9, 8, 7, 6, right? And we have an extra point there. So this is actually a longer path than this one. And now we've explored these two possible paths, right? For this node, which is the first node we just did, all of these things are on the closed list. We don't want to explore these paths again, these nodes again. All right. Well, what about if I go here? So this is now I come back to this part, right? And then I start doing this one. Okay, well, I want to come down here. This is the same. Can't go over here. And we do this one, and we do this one, and then we come back to this one, and we say, well, this one is 10, 9, 8, 7, 6, 5, 4, 3. It's the same as this one. So really, this path here, the orange path, is the shortest path. Why? Because we don't explore these ones at all, because we don't care to explore them, because we found the smallest path, and we can't go through these tiles. Make sense? They're infinite because you can't go through them. They have an infinite cost, Devin, because these are a block, some kind of wall or something else. And they're infinite because if I compare 8 to infinity, then 8 always wins. Smallest. Does that make sense? Questions around Manhattan distance and how that is different from Euclidean distance. So that's how they work, and we use these estimation heuristics in order for us to determine the shortest path, and we add that up to, for example, we can also layer on top of here terrain costs. So if we had, let's say around here, one more thing, just to kind of add some additional challenge for you guys to think about. And you should play around with this in your head, try it out, and try using the same grid just from the PowerPoint slides here, and try and think about this. If I had undo that, change. If I had a river that ran this way, right? You can go across the river if you want to. It had another path that went this way, and let's say the river also kind of went this way and also here. So some kind of weird river that went this way, and maybe it kind of ran up this way too. Okay, so there's the river, and the river had a cost path of 3. So the actual movement from one tile to the other costs 3, right? And let's suppose in your tile map, I'm not going to do this calculation for you, but I want you to explore this with me, this thought, okay, before we leave for today. And let's suppose that the green paths here represented a cost of 1. So these are a cost of 1, right? And we have a bridge that goes over the river, right? So that bridge, you can actually traverse the river. And maybe this is the one path that is smallest, and maybe there's a bridge here as well. Let's make a bridge here and a bridge here. So the bridge cost is going to be, we're going to kind of mix the two values up like this, so you can see the costs. So anywhere where there's bridges like this, the cost is 2. So this is 1, this is 2, and the blue is 3. Okay? And let's suppose anywhere here, here, or here, right? Let's just make sure the path here is green. So we'll make sure the green path goes here, and there's a green path here, right? And there's a green path here and here. But anywhere outside those areas, it's difficult terrain, right? Maybe there's woods or mountains. Well, not mountains, but let's say hills, right? So these are other areas here. Difficult terrain is the same cost, or maybe a higher cost, than walking through the river, because you can walk across this little stream. Let's say this is a stream, not a river, but it's something that looks like this. Okay, there we go. So then, and there's no cost to get here. Okay, this is like the green cost, like we said before. So something like one of these. And if I was to say what these things mean, again, the light green is 1, the blue squares are 3, the bridge squares are 2, and the dark green squares are, we'll call them 4. Make them even higher. When we take this into account, we add the movement cost, and we add on the heuristic, all right, to create the total cost, the total path cost, from one square to the other square. And this is where Alex and I have asked you to make an interesting map. Interesting map means don't make all the path costs 1, please. That's not what we're asking you to do. We're asking you to do, we're going to show you everything as 1. The whole grid is equally weighted. right? And we're not even talking about obstacles here. You can also add an obstacle. Let's just use an obstacle like black, right, to denote some kind of mountain. So this is an obstacle, right? And maybe there's another obstacle there, like some kind of mountain or other obstacle, right, that kind of stops you from going to these places, right? So impassable. Those are impassable parts of the tile, right? How would you figure this out now? And chances are, if I was going to guess how this would move, just from what we just did, our little adventures in movement, right? And let's use a dark tile number like blue. Well, actually, blue is also taken. I don't have a lot of choices here. Let's use purple. There we go. So chances are, what it would do is do this, move across here, right? It would look at this as impassable, right? There's a bridge, but there's a bridge to something that's impassable for us. You can't go. Maybe there's a building here, and the building has a bridge across, okay? So it would probably go this way, right? Across to this. And then from here, because it would calculate what it is, it would go across this way, right? Until it got to this point here to make a decision. It can't go this way because the cost is longer. It's farther away. This square is farther away than this square, right? And this square is higher cost than this square. So it immediately would go across this way, and it would come to this point here. And it would say, okay, so now that I'm across this way, well, I can also go here, let's say, right? I can go here or here, but I would, in a right winding format, I would take me to this particular square. And so you can clearly see that going up is longer, going down is more cost, and it would kind of march me across this way. And now I wouldn't go here because it's a higher cost. I'd go this way and this way. That would be the path that I would make just by looking at it. And that's the way you can test it too for you and your games. Okay? Make sense? All right. So that is my little demonstration for this part. Let's talk about Lab 4 for this week. So Lab 4 is going to be a couple things. We're going to start cleaning up the scene. Again, Lab 4 is the beginning of Lab 4, right? So this is kind of like the first set of goals for Lab 4. We're going to have another week of Lab 4, right? So we're going to clean up the scene, remove the obstacle, stop the starship from seeking, because the starship's been seeking, or the spaceship's been seeking this whole time. Remove previous UI elements from the IM GUI. We're going to clean up the scene. That's one of the things we're going to do. We're going to create a tile class, right? Then we're also going to create something called a grid of tiles, and we're going to show them using IM GUI. Some way of showing these grid of tiles using IM GUI. And then, this is the difficult part, we're going to snap our spaceship, right, and our target to the grid. That's all I want to do for this week. And setting this up will take most of the time, believe it or not. Okay, so that's our goal for Thursday when we get together. Questions before we go for the day? All right, guys, just to summarize what we talked about today, we talked about Astar Pathfinding and Dijkstras Algorithm. We talked about how Dijkstras Algorithm is great if you want to explore the world. If I want to explore the world and maybe I have sub-goals, maybe I'm going to use Dijkstras Algorithm, where it kind of does a pattern fill that looks like this, okay, where it kind of slowly gathers every information about the entire game world. Even when there's an obstacle, it'll go around it, but it'll explore as much of the game world as possible while it's moving towards its goal. That's what it's going to do. Okay, that's what we talked about when we said Dijkstra's algorithm. And you can clearly see that it explores almost more than half the map, even on this side and this side. It doesn't care about the distance necessarily. It cares about making sure 100% that we find the shortest distance. And until it finds the shortest distance, until these parts, we know that these parts are longer, then we keep going, we keep expanding. And that's the pattern. Whereas for Astar, you can see that it is very more directed. It uses a point-to-point algorithm. It does still do expand and explore things, right? It really depends on the heuristic that we're using. This could be something like Euclidean distance, the way it's been done here, right? Because we're able to explore in a diagonal fashion, but it will definitely find the path faster. Does it explore as much of the world? No, but it's great from point-to-point exploration, point-to-point pathfinding. Okay, that's what we talked about. We talked about a couple of different data structures, and we talked about a couple of heuristics, the Euclidean distance heuristic with a different fill pattern than the Manhattan distance heuristic. And what I said was Manhattan distance is better when we only have a choice of going to have 4 neighbors, up, right, bottom, and left, as opposed to all the neighbors, 8 neighbors. 8 neighbors, we want to use Euclidean distance. 4 neighbors, we want to use Manhattan distance, because we can't go in a diagonal fashion. Okay? Questions before we go for the day? All right, I'm going to stop recording on YouTube and take any other kind of administrative questions, and we'll see you on Thursday for those people who are here. All right, guys, thank you so much. If you have any questions,